thing I want to do is to go through the three major theories of acids and bases. The three major theories of acids and bases. Okay. All right. And the first one is the one we've been using all year. And that's the Arrhenius acid-base theory. The Arrhenius acid-base theory. And in the Arrhenius theory, an acid is any chemical species that gives up or donates a hydrogen ion to water. A chemical species that gives up or donates a hydrogen ion to water. And then an Arrhenius base is any species that gives up or donates a hydroxide ion to water. An hydroxide ion to water. So then our next major acid-base theory is called Bronsted-Lowry. Bronsted-Lowry. In the Bronsted-Lowry theory, an acid is any chemical species that donates a hydrogen ion to a covalent bond with a second species. An acid is anything that donates a hydrogen ion to a covalent bond with another species. If you will recall, hydrogen ions are hydrogen atoms that have lost their electron. So they would have covalently bonded with something else and shared its one electron with something else, but leaves without that electron it shares. So when it leaves, it's just a proton. Okay, so it's donating a proton to a covalent bond with another species. But remember, it left from something where it shared two electrons. Okay, and so it's going to go to something where it's going to share two electrons. Okay, so when it covalently bonds, the thing it has to covalently bond with has to have two electrons available, a pair of electrons available for that covalent bond. Now, a Bronsted-Lowry base then is that chemical species that has the pair of electrons. So it is a chemical species that accepts that hydrogen ion in a covalent bond. Okay, a Bronsted-Lowry base is a chemical species that accepts that hydrogen ion in a covalent bond. And then our last major acid-base theory is the Lewis theory. You probably remember Lewis. You don't remember Lewis? What do you remember about Lewis? Formulas? Lewis formulas? Okay, all those electron dots. Well, it probably won't surprise you to know that Lewis, those electron dots, of course, represent electrons, and so Lewis defined acid behavior by the electrons. Okay? So in a Lewis theory, an acid is a chemical species that accepts a pair of electrons in a covalent bond. An acid is a chemical species that accepts a pair of electrons in a covalent bond. And in the Lewis theory, a base is a chemical species that has a pair of electrons that it shares in a covalent bond. We call it donating a pair. It doesn't mean it's giving them away when we say donating. We mean that it's donating a pair of electrons to the bond. It doesn't give them up. It just shares that pair of electrons in a covalent bond. So a Lewis acid accepts a pair of electrons in a covalent bond, and a Lewis base donates or shares a pair of electrons in a covalent bond. Okay? So this is not the same thing as covalent bonding, where we first described covalent bonding way back in Unit 3 as one atom coming to the bond with an electron, another atom coming to the bond with an electron. They share those two electrons. This is different. In this case, the pair of electrons comes from one species, and you don't have one from one species and one from the other. You have both electrons coming from one species. Okay? And so the one that has the electrons that brings to the covalent bond, that's the base. The thing that comes there without that pair of electrons, that shares that pair of electrons, is the acid. Okay? Everybody with me? Now, all Arrhenius acids and Arrhenius bases would also be Bronsted-Lowry bases and acids. But not all Bronsted-Lowry acids and bases are Arrhenius acids and bases. So this is a more inclusive definition. More things would be called Bronsted-Lowry bases and acids than would be called Arrhenius acids and bases. Okay? And the same is true with Lewis. There are a lot more things that would be Lewis acids and bases that would not be Bronsted-Lowry. All Bronsted-Lowry acids and bases would also be Lewis acids and bases, but not all Lewis acids and bases would be Bronsted-Lowry acids and bases, and would not all be Arrhenius acids and bases. Okay? So each of these becomes more inclusive, to the point that Lewis acids and bases would fit our definition of salts. Many salts that we've defined in previous units would also be Lewis acids or Lewis bases. Okay? And that makes a lot of sense when you understand acid and base behavior, because a lot of salts will create a solution that has acid behavior and base behavior. Okay? So when you understand all that, it makes Lewis make a lot more sense. But Lewis is a bit more complex, and we won't get into Lewis a lot. Okay? We'll only learn to define Lewis and be able to show or illustrate using Lewis dot formulas what a Lewis base or acid is without getting into some of the details on Lewis. We'll spend a lot of time on Bronsted-Lowry. And up until this point, all of our acid work, all of our definition of acids and understanding what acids do were based on what Arrhenius does. Okay, that was based on the Arrhenius definition, where we give up a hydrogen ion to water. So when we were doing complete and net ionic equations, acids split up into hydrogen ions and whatever the anion was, and you showed them as being aqueous, H plus with an aqueous symbol. Okay, and that's an Arrhenius acid behavior for Arrhenius acids. Okay, all that was Arrhenius acids. And if we had a base where we had like sodium hydroxide would split up, you get hydroxides out in water. Well, that's Arrhenius base behavior. Okay, everything we've done so far has been Arrhenius acid base behavior. Now we're going to get to a lot of Bronsted-Lowry acid base behavior, and we'll discuss in a limited form Lewis. But we'll spend an awful lot of time understanding Bronsted-Lowry in this unit. You with me so far? All right then. Let me throw a couple of equations at you, and let's see if we can define, by looking at the equation, what kind of acid or base it is. Is it an acid? Is it a base? And which definition does it fit? Okay? So let's start with this. This is one of the two acids you used in the last lab. So what I'm doing is I'm taking hydrogen chloride, which in its pure form is a gas, at least at average temperatures and pressures is a gas. We're going to put it in water. So we're going to show it as being put in water. So whatever change is taking place in water. That's what this kind of symbol means here. And as a result, we're going to get hydrogen ions, which are aqueous, and chloride ions, which are aqueous. So this goes back to complete and net ionic equations. We learned to split up acids into separate ions of hydrogen and whatever the anion was. Okay? All right, look at your definitions then of acids and bases and tell me, is this an acid or base? And if so, which definition does it fit? Does this kind of illustration of acid behavior or base behavior fit either acid or base behavior? And if so, which definition does it fit? All right, so the argument is that it's an Arrhenius acid. Okay, can you tell me why it's an Arrhenius acid?
Because it's donating a hydrogen ion to water.
donating a hydrogen ion to water. There you go, pretty simple. Make sense? And Arrhenius is the simplest of the definitions. Okay? So this is a way of illustrating Arrhenius acid behavior. Okay? All right, let's look at this one. All right, here we have sodium hydroxide. Again, we're putting it into water, and just like when we did complete and net ionic equations, sodium salts would split up completely. All right, they're completely soluble, so they break up into sodium ions and hydroxide ions. Hydroxide is one of the polyatomic ions you're supposed to have memorized in this class. So if you don't know it's a hydroxide ion, go back and look at all those flashcards I gave you to memorize with. Okay? So looking at this equation then, does this illustrate acid behavior, base behavior, and whether it's acid or base behavior, which definition does it fit? What now? Arrhenius? It's an Arrhenius base. And why is it an Arrhenius base? It's donating a hydroxide ion to water. Okay, so it's an Arrhenius base. And if you're trying to figure out how to pronounce Arrhenius, this is what a pirate says. This is a female yard bird. And this is you and me. Okay? Arrhenius. Okay. Arrhenius. All right. I know. That's okay. You can say it weird. It's fine. Okay. I might be pronouncing it wrong. You know, the fact is that, you know, he wasn't an American. You know, he wasn't born in South Carolina, so he might pronounce his name, you know, differently than I'm used to pronouncing it. It's the way I've heard it pronounced for years. Now this is going to require a little more thinking, so you got to put on your thinking cap and be creative in how you look at this. All right, kind of sort it all out. You got to be a bit of a detective here. I want you to look at this equation now and tell me, does this equation illustrate acid behavior or base behavior or maybe even both behaviors? And if so, which definition does this illustration fit? All right. So the argument is that this is a Bronsted-Lowry acid behavior illustration, where the hydrogen from hydrobromic acid is going to leave the hydrobromic acid. It's going to join up and covalently bond with this water molecule, which has, even though we don't illustrate it here, the water has two lone pairs of electrons. It's going to join up here and covalently bond with this water, particularly with the oxygen in the water, and form H3O. Which is behavior that we described as being Bronsted-Lowry. It donates a hydrogen ion to a covalent bond with another chemical species. Does that make sense? All right. Is that the only behavior it illustrates? What is the definition of a Bronsted-Lowry base? It accepts a hydrogen ion. So the water here is accepting that hydrogen ion, right? So this is the Bronsted-Lowry acid. What is this? That's a Bronsted-Lowry base. Does that make sense? Because this is donating the hydrogen ion, and this is accepting that hydrogen ion. This is the acid over here, hydrobromic acid, and the water is a base. All right, everybody with me so far? Okay, here's the bailiwick. All right, I put an extra hydrogen on this water. Now, water isn't particularly stable with that extra hydrogen on there. That hydrogen can leave. If that hydrogen can leave, where would it go? Over here, right? So this is also an acid. And this, because it can accept a hydrogen ion, because it's negatively charged, this is also a base. And it's got lone pairs to accept it with. Okay? It can covalently bond with that. And so this then is also a Bronsted-Lowry acid, but it's called the conjugate acid of this base. Okay? Wherever that hydrogen ion joins up with, wherever it ends up with, okay, that creates a Bronsted-Lowry acid that's the conjugate of the base. So when the hydrogen ion leaves here, it joins up here, and when it joins up here, it creates an acid that is the conjugate of this base. So Bronsted-Lowry conjugate acid, even though my writing isn't too great there. Bronsted-Lowry conjugate acid. This then, since it will accept a hydrogen ion, is a Bronsted-Lowry conjugate base. So in the Bronsted-Lowry system, every acid has a conjugate base. The conjugate base is what you have when the hydrogen ion leaves. Okay? In the Bronsted-Lowry system, every acid has a conjugate base. The conjugate base is what you have when the hydrogen ion leaves. All right? Every base has a conjugate acid. The acid is what you get when the base covalently bonds with the hydrogen ion. So this is the base because it accepts a hydrogen ion, and once it accepts that hydrogen ion, it becomes a conjugate acid. All right? Well, it can work with other acid-base theories, but it's the only one we talk about like that in this class. Okay? We could do that with Lewis acids and bases. We could do it with some Arrhenius acid and base behavior, but we generally don't use that terminology for Arrhenius. We can use it for Lewis, but we won't get into it in Lewis in that context. We're going to limit our Lewis discussion to just what a Lewis acid and base does and being able to illustrate it. Okay, not actually using it a lot. All right? You with me? Okay. But this also turns out to be a Lewis acid. In addition to being a Bronsted-Lowry acid, it's a Lewis acid. And let me show you one. What's the definition of a Lewis acid? I gave you the definition of a Lewis acid. You should know the definition of a Lewis acid. So it's a chemical species that accepts a pair of electrons in a covalent bond. All right? So let me show you how that works. Let's do it in Lewis dot form. Okay? Write this formula in Lewis dot form. I won't let you write this formula in Lewis dot form. Units 2 and 3 are coming back again. Okay? Lewis dot form for this formula. Write this formula in Lewis dot form. And then when you do that, write this formula in Lewis dot form as well. So both the hydrobromic acid and the water, I want you to write in Lewis dot form. Okay, so here are the two Lewis dot formulas for these two formulas here. Hydrobromic acid would look like this, and water would look like this. Okay? All right, in order to get to this formula, we would have a water that has gained an extra proton, and it gets the proton from here. That makes sense? Everybody with me? And so when you add another proton, you get a positive charge. Actually, the positive should go outside that, not inside that. Okay, so here's what happened. The hydrogen ion left this species just like it did up here. Okay, the hydrochloric acid split up. You got hydrogen ions and chloride ions. Here, the hydrogen is going to leave the bromine. Okay, so the hydrogen ion's leaving. And it goes over here and it accepts that pair of electrons from the water in a covalent bond. And isn't that the definition of a Lewis acid? A species that accepts a pair of electrons in a covalent bond. Okay? And so this is the Lewis acid because the hydrogen that accepted that pair of electrons that came from here. Okay? This is the Lewis acid because the hydrogen ion that came from this is what accepted that pair of electrons. Okay? This then is the Lewis base. Why? What's the definition of a Lewis base? Huh? That's the Bronsted-Lowry base you're defining, I think. It donates a pair of electrons or shares a pair of electrons it has. This is what's happening right here. Okay, with another chemical species. Well, this is the species that has a pair of electrons that it shares, so this is the Lewis base. Okay? And as a result, then we're going to get a bromine, a bromide ion. Okay? And so here's our Lewis acid and Lewis base. When this formula formed, hydrogen came here because the hydrogen atom had one electron, so it brought one electron. Bromine had 7 electrons, so it shared one electron. The hydrogen and bromine both shared an electron to give the whole thing 8 electron dots. When the hydrogen leaves, it leaves without that hydrogen, that electron that it brought. So since it leaves the electron behind, now the bromide has 8 electrons instead of 7. And that's where the negative charge comes from, the extra electron. Okay? The charges are from an imbalance in the number of protons and electrons. You with me? All right. Like I said, we're going to spend a lot of time with these kinds of acids and bases here. Okay? Not a lot with these. This is about the level of what you need to know in Lewis. Okay? About the level of what you need to know in Lewis, in the Lewis theory. We'll be spending a lot of time with Bronsted-Lowry. Okay? We'll spend some time with Arrhenius. But we've been spending most of our time with Arrhenius. We don't need to spend a lot more time with that. We need to spend a lot more time with conjugate acids and bases and so forth. Okay? Questions, if any, so far? All right, then. Let's talk about strong acids and weak acids. Strong acids and weak acids. And let's define those. Those are important. Okay? Strong acids So let me tell you what they aren't first. So let me tell you what they aren't. Because I know when you come to high school chemistry, the way that you were taught about acids and bases, most of you anyway, led you to the conclusion that strong acids had a really low pH, right? That's wrong. Okay? Strong acids can have a low pH, but that's not the actual definition of a strong acid. Okay? The actual definition of a strong acid in chemistry is an acid or chemical species that has hydrogen ions, and those hydrogen ions dissociate or break off completely. Okay? A strong acid has hydrogen ions, and those hydrogen ions break off, or the word is dissociate completely. Now the word dissociate is like the word associate or associate, okay? But you just put DI on the front instead of A, okay? And the word associate can be pronounced associate if you're talking about people getting together. So if I associate with you guys, it means I hang around with you. If I disassociate from you guys, I stop hanging around with you. That make sense? They dissociate completely is the word, okay? So a strong acid has hydrogen ions, and those hydrogen ions dissociate completely, okay? And so, by extension then, a weak acid does not dissociate completely. Okay? I don't know if you need to write that definition down or not, but you should be able to figure it out from that definition. A weak acid does not dissociate completely. Okay? Now, when I use the word completely, as is often the case in chemistry, that's not an absolute term. Okay? It means that virtually all the hydrogen ions will dissociate. Doesn't mean that every single one always does. All right? All right, let's go to what a strong base is. So a strong base is a species that contains hydroxide ions that dissociate completely. A strong base is a chemical species that contains hydroxide ions that dissociate completely. Now, when I'm talking about hydroxide ions dissociating completely, I'm talking about Arrhenius acid-base behavior, because Arrhenius acid-base behavior talks about hydroxide ions being broken off and joining up with or dissolving in water. But it also fits all the other definitions. There are no strong bases that don't fit this definition, even in the Arrhenius and Bronsted-Lowry systems. Lewis and Bronsted-Lowry systems, okay? All right, so a strong base has hydroxide ions that dissociate completely. This is a list of strong acids and bases that you must know. Okay, in this class, you must know these strong acids and these strong bases. Okay? If you want to memorize them, that's fine. Memorize them. But you must know they're strong acids and bases when you see them. All right, so memorizing these is a great idea, but you know what? There's a way to look at the formulas and kind of tell. So let me give you sort of a simplified way of recognizing when you have strong acids and bases, okay? First thing, we have to classify these acids as either binary or oxyacids. And that's the same thing we did when we were naming acids when we first began doing that way back in Unit 4, okay? We classified acids as being either binary or oxyacids, okay? The binary acids are the first three in our list here under the acids, where we have just one or two elements. Okay, binary means two elements. It doesn't mean two atoms, but it means two elements. Okay, well, the strong binary acids, as it turns out, do have just two atoms. Okay, but can you see anything in common in those acids? What do they have in common? Well, there's hydrogen there. That's one thing. What else do they have in common? What? They're all from the same, the anions are all from the same column. Is that what you were trying to say? Okay. So let's look on your periodic table down here. Okay. And notice that in the halogen column, all the strong acids have halogens as the anion. The anion being the negative part. Okay. Anions are the negative ions. Ions are charged particles. Anions are negatively charged particles. Now, the key thing is that these are the halogens in the middle. Okay, so the strong acids have halogen anions in the middle. Okay, the strong acids, at least the strong binary acids, have halogen anions in the middle. Does that make sense to you? That's for the first three up there and not for the last four. But that's how to recognize a binary strong acid. It has a halogen anion that is in the middle, having to do with where they are on the periodic table in column 17 or column 7A. Got that? Let's look at these others then, all these oxyacids. And they're called oxyacids because they contain oxygen. They contain polyatomic ions that have oxygen in them. And what all these polyatomic ion acids have, these oxyacids have in common is this, that the number of oxygen atoms in the formula exceeds the number of hydrogen atoms in the formula by 2 or more. So a strong oxyacid has 2 or more oxygens more than the number of hydrogens. Okay? A strong oxyacid has 2 or more oxygens more than the number of hydrogen atoms in the formula. Now, for the strong bases, there isn't any little, pithy saying or anything to help you memorize those. You just got to know what those are. I mean, if you wanted to be kind of, twist the point a little bit, you could say NAKBACA. You could put all those together into some kind of strange word, Nakaba or something. Okay, if you want to try to figure out which one are the strong bases, they're the hydroxide salts that have Nakaba as a cation, if you want to do it that way, okay? Because cations are the positively charged ions, all right? Got that? So there's no magic formula for that, no pithy saying or anything. You just got to know those, all right? Those are the strong bases that you need to know in this class. Any questions about that? All right, then. If strong acids are those that dissociate completely, then weak acids do not. And we're going to look at some weak acid behavior, including the kind of acid and base behavior we had in the last lab. Now, if you looked at that list of strong acids, you know that one of the 2 acids we used in the last lab was a strong acid. Okay? And strong acids dissociate completely. All right? So this is actually, in its pure form, at normal temperatures and pressures, this is a gas. And if we're using the Arrhenius system, then it breaks up completely into hydrogen ions like this. Oh, that should be aqueous, not gas, aqueous. Okay. All right. If we're using the Bronsted-Lowry system, we would do this. Okay? But it completely dissociates. Virtually completely. Meaning that for every single molecule of hydrogen chloride that I put in water, every single one of them will break up. Either they're going to break up in this fashion in the Bronsted-Lowry system, or this fashion in the Arrhenius system. Now, when I say in this system, this is a way of thinking about acid-base behavior. In fact, neither one of those is a complete picture. The real behavior of these hydrogen ions is a bit different. What happens is the hydrogen ion does break up in water, and it does covalently bond with water molecules, but it forms this hydronium, and that's what the name of this is right here, hydronium. It forms this hydronium, and that hydrogen ion pops off of there and goes to another water, and goes to another water. It bounces around in there. It's never really sitting out here by itself, as is represented by the Arrhenius theory, but it never is completely joined up with and solidly or securely joined up with any single water molecule. Okay? Got it? It keeps bouncing around in there. All right, so these are ways of thinking about the behavior, though, and why we have these different theories. Okay? All right, so this is a strong acid because almost every single hydrogen ion breaks up here. So for every one of these hydrogen chlorides I have, it's going to produce 1 hydronium and 1 chloride ion. Or in the Arrhenius system, for every hydrogen chloride molecule I have that I put in water, it's going to produce a hydrogen ion and a chloride ion. 1. A singular. One of these makes one of these and one of these. Okay? One of these sheds that hydrogen ion, it joins up with water, so every time I have one of these, it will become one of these and one of these. You with me? All right. So one of these produces one of these and one of these every time. One of these produces one of these and one of these every time. Okay? Weak acids do not dissociate completely. What was the weak acid we used in our last lab? Acetic acid. Okay? And that formula is this. And let's see, let's use the Arrhenius theory first. So the hydrogen ion is going to come off. If the hydrogen ion comes off, it leaves behind this. And what is this thing called? One of those polyatomic ions you're supposed to have memorized for this class. Huh? Acetic. Okay, yeah, I can hear you pronouncing it a little differently than it's normally pronounced. That's called acetic, an acetate ion. Okay, acetate ion. All right. So hydrogen ions and acetate ions. This is the Arrhenius theory system. Okay, if we're going to do this in Bronsted-Lowry, we've got to have that hydrogen ion pop off of there and join up with a water molecule. Oh, no, I don't want any plus sign there. I'm sorry. Wrong place for the plus sign. It's over here. There we go. All right. So, but it doesn't break off completely. At least that's the definition we used. The reality is a bit more complex than that, but it relates to the stuff you learned in the last unit about equilibrium systems and Le Chatelier. Okay? So, what is actually happening here is not that this is not completely breaking up. It kind of isn't completely breaking up. But all of these are continuing to break up, while at the same time, these are reforming this stuff. So it's really going in both directions at the same time. Okay? When you reach a point of equilibrium, where as many of these as can break up have broken up, what's really happening is these continue to break up, and these are continuing to reform this. Okay? These are continuing to react this way, but these are also reacting in this direction. And so this is an equilibrium system which obeys the Le Chatelier principle. Okay? It's going in both directions, and that's why we have a double arrow here. Okay? Weak acids, we show a double arrow because that's what's really happening, that the reaction is moving both forward and backward at the same time. Now, what happens is initially when you first put the acetic acid in the water, you don't have an equilibrium system at that point. You're only having things go in one direction. But eventually, there's enough of the product stuff, at least in the equations, the product stuff, what's represented over on the right-hand side, that those are constantly reforming to a point where you reach a point where the rate at which the forward reaction equals the rate of the reverse reaction. Okay? Everybody with me so far? All right, so that's what an equilibrium system is. And Le Chatelier, the principle, is that, or states that, a system in equilibrium like these will remain in equilibrium unless some pressure is added to the system to unbalance the equilibrium. Then the equilibrium reforms a new point of equilibrium, a new balance point. So when we were talking about dissolving things in the last unit, and we had a saturated solution, and we had some of the solute that hadn't dissolved that was still sitting on the bottom, we said that the solute continued to dissolve, but at the same time, the solute that was in the solution kept depositing, and the rate at which the dissolving occurred equaled the rate at which the depositing occurred. So it looked like the amount of stuff in the solution didn't change. Okay? Same is true here. This looks like the rate of forward reaction equals the rate of the reverse reaction. But if I do something that changes things around a bit, it might be temperature, it might be something else, that it'll change the point of equilibrium. Okay? If I heat this up, yeah, we'll probably make more product. And so it'll unbalance things, and you'll get more product being, reactants being dissociated until the point that the forward reaction again equals the reverse reaction. Okay? That's what an equilibrium system is. All right, you with me? So temperature can affect this equilibrium as well. Now, so this stuff up here at the top completely dissociates. Both these equations represent what's happening with hydrochloric acid. This is what's representing happening with acetic acid. This does not dissociate completely, or doesn't appear to. Okay? Here's what happens in our lab in the last class, the last time we did a lab. Since this dissociates completely, when I put hydroxide or sodium hydroxide in there, It's pretty straightforward. It completely reacts with all the hydrogen ions and neutralizes everything. Okay? So here's sodium hydroxide. And sodium hydroxide, which is a solid, it breaks up into sodium ions and hydroxide ions. And those hydroxide ions, I'm sorry, that's a negative sign. React with the hydrogen ions here, or the hydronium ions. Let's do the hydrogen ions first. And what do they form? H2O. That's how it neutralizes it. Okay? Or if we're using the Arrhenius, I'm sorry, this is Arrhenius. The Bronsted-Lowry system, here's our hydroxide here. And we have hydronium, H3O plus. Well, when those react together, what do you get? You still get water, but instead of one of them, you get two of them. Okay, so we really need two of these. No, that'd be right, because one hydrogen comes off of there and joins. That's right. Okay, so you're still neutralizing it, whether you're talking about Arrhenius here or Bronsted-Lowry here. Okay, that's the way that neutralization occurred. Now, in order to get the pH the same when we started the last lab, we had to have the same number of hydrogen ions in the solution. Since this one didn't dissociate completely, the number of hydrogen ions meant that we had a whole lot of these still in the water, because these don't dissociate completely. To get the same number of hydrogen ions for this solution and this solution, all of these dissolved. So there's none of these left, right? There's still a lot of these left, because to get the same number, this doesn't dissociate completely. You could have more of these to start with. You with me so far? All right. So every time I neutralize one of the hydrogen ions down here, that unbalances the equilibrium. And more of these break up to replace that hydrogen ion. So every time I neutralize a hydrogen ion, one of these breaks up to replace that to continue that equilibrium. And so every time I use up a hydrogen ion here, this equilibrium replaces it, so the reaction keeps moving in this direction. So you have to keep putting more and more sodium hydroxide in the water, in the solution, to neutralize the hydrogens, but then the acetic acids keep breaking up to make more hydrogens. That's why it took a whole lot more sodium hydroxide solution to neutralize the acetic acid solution, because you had to keep breaking more of these up until finally you used them all up to make nothing but water to neutralize everything. Okay? Now, if you're zoning out on me here and you're not following along what's going on, you're not imagining these molecules moving around, okay, then this is going to be tough for you on the test. But if you can run that movie in your head and see this happening, it's going to help you a lot. Okay, you're going to understand the behavior of weak and strong acids. It'll help you a lot if you can do that. Let's take a look at a bit of an illustration here for strong and weak acids, okay? All right, so here's our strong acid, all right, where we have hydrogen chloride in water, but they haven't, this is like when we just put them in there and we've frozen time, we stopped time, and they haven't yet broken up. Okay, but they're going to dissociate completely, right? All right, so once the hydrogen chloride is put in the water, all of these break up into separate hydrogen and chloride ions. Okay, you see that happening here? Okay, so every single one of these breaks up. We don't have any hydrogens, any hydrogen chloride left anymore. Everything's broken up. Got it? So whatever the pH is, it's measuring the number of hydrogen ions here. Okay, so let's look at our acetic acid. Here's hydrogen and the acetate ion joined together. All right, but only some of these are going to break up. Okay, only some of them are going to break up. There's a lot more of these acetic acid molecules still together than there are hydrogen ions in solution here. Got it? To get the same pH, I've got to have a whole lot more acetic acid molecules than I had of hydrogen chloride molecules. Make sense? Because the pH measures the number of hydrogen ions in the water. And you can see from here, there aren't a lot of hydrogen ions in this water as compared to the last illustration. So to get the same pH, you've got to have a lot more of this stuff than I have with the hydrochloric acid. But at the same time, to neutralize this, every time I put sodium hydroxide in there and they react with all these hydrogen ions, another one of these hydrogen acetate or acetic acid molecules break up again and make more hydrogen ions. So I keep putting hydroxide in there, neutralizing the hydrogen ions, and more hydrogen ions get made. Until finally we overwhelm or use up all of the acetic acid, and then we can neutralize the acid. That makes sense? Now that's the secret behind what's called a buffer. Okay? That's what a buffer does. That's what a buffer does. A buffer resists change in pH. A buffer resists change in pH. So the acetic acid system here, whether you're using the Arrhenius theory illustrated by this equation or the Bronsted-Lowry theory illustrated by this equation, creates a buffering system. It resists change in pH. And some of you complained when you first started trying to neutralize the acetic acid, the pH isn't changing, Mr. Tedder, something's wrong. No, nothing was wrong. It was doing exactly what it's supposed to do. You with me? Now you have two different pH systems, or buffer systems rather, in your body that keeps your blood pH at about, what's your blood pH supposed to be? 7.4, 7.2, 7.4, in that neighborhood. Okay? And so what we have is a system of buffers. These are really acids, weak acids that do this. Okay? That keep your blood pH where it should be. If your acid content in your blood gets too high, as in what happens when you don't get enough oxygen, okay? The carbonic acid level builds up and you faint, okay? And you faint and your body kind of reboots like a computer reboots, and you start breathing normally, and the carbon dioxide gets taken out of your body and your blood pH goes back where it's supposed to be, and then you wake up. Okay? On the other hand, if you hyperventilate, you get too much oxygen, in which case the pH gets to be too high. Guess what happens? You faint. You faint. You can breathe normally. Everything gets back to where it's supposed to be, and you wake up again. Okay? So that system is an equilibrium system based on buffers, just like in this lab. Okay? Very similar to this lab. All right? Which is where you're going to get the thing we're going to talk about for your homework, and that is that you're going to take one of these buffering systems, phosphoric acid. You're going to take phosphoric acid and write all the dissociation equations for phosphoric acid. Now, this is a dissociation equation. This is a dissociation equation. Okay? These are all dissociation equations. Before you're ready to do the homework, I want to show you a different dissociation set of equations that apply to an acid that is somewhat like phosphoric acid, all right, in some respects. The difference is phosphoric acid is a weak acid, and the acid I'm about to show you is a strong acid, okay? All right. Let's look at the strong acid, sulfuric acid. And we're going to use the Bronsted-Lowry way of representing equations here. So we're going to show it being reacted with a water molecule. Okay? Now, the difference between this acid and the ones we've looked at so far today is that this acid has two hydrogens that can dissociate. This acid has two hydrogens that can dissociate. In both the hydrochloric acid here and the acetic acid here, they just had one hydrogen that could dissociate. Now, acetic acid had a number of different hydrogens here, but these hydrogens that are attached to this carbon, they don't dissociate. In reality, acetic acid probably ought to be written more like this, which is the way that an organic chemist would write it, because the hydrogen ion is actually attached to an oxygen. That's the hydrogen ion that pops off to form an acid. If we were doing this in the Lewis formula system, remember Lewis dots we just did a minute ago? Let's do a Lewis formula instead of Lewis dots here. So I'm going to have the shared pairs of electrons replaced with lines. So these three hydrogens, up here they look like right there. Okay, these three hydrogens are attached to this carbon. This carbon is attached to another carbon, and that carbon has two oxygens on it. Okay, one of those oxygens is double bonded, and the other oxygen is attached to our hydrogen. Okay, so this is a Lewis formula for this same acid and this same acid we have up here. Okay, and in this form, you can see a lot more easily that this hydrogen is the one that actually leaves when the acidic behavior occurs. So the negative charge actually exists on this oxygen right here. Actually, some other things happen too. We don't talk about much in high school chemistry. Okay. All right, you got that? Or at least in the first class, first level of high school chemistry. All right, back to our sulfuric acid then. There's two hydrogen ions that can dissociate, not just one. All right? Let's take the first hydrogen ion off because that's what actually happens. In reality, both hydrogen ions don't leave at the same time. They leave one at a time. This hydrogen ion, we're going to take one hydrogen ion off. If we do that, what's going to be left is HSO4 with a 1 negative charge. Okay? And then we've got a hydrogen ion that pops off of here and joins up with the water, and we get H3O plus, or hydronium is what that's called. This species here, H3O plus, is called hydronium. Okay? Now, this is called hydrogen sulfate, or bisulfate. All right? Sulfuric acid dissociates using the Bronsted-Lowry system. Then we have bisulfate and hydronium. Got it? Then this hydrogen can also pop off of there. Now the difference is all of these first hydrogens are completely dissociated. All of these first hydrogens are completely dissociated. The second hydrogen, this one right here, is not completely dissociated. So this acid represents a system where you have a strong acid and weak acid all kind of bundled up in one. Okay? This is a strong acid, but only for the first time a hydrogen pops off, for the first dissociation. You with me? It's a strong acid only for the first acid that comes off, only therefore for the first dissociation. This is also an acid, so this hydrogen sulfate, which has a negative charge, that hydrogen can come off of that and join up with another water molecule. And now we get just a sulfate ion and another hydronium. This, however, is a weak acid. This right here is a weak acid, so we've got a weak acid system and an equilibrium system being set up. So in a weak acid system, we've got an equilibrium going on, which means at the same time, or there's a point at which this acid has broken up enough that we've got enough of this stuff in the solution, and the rate at which these are reforming over here is equal to the rate at which these are breaking up over here. Okay? And when that occurs, then you have a true equilibrium. Until it's balanced and the rate of the forward reaction equals the rate of the reverse reaction, you don't actually have an equilibrium. When equilibrium occurs, the rate of breakup equals the rate of makeup. Okay? The rate of breakup equals the rate of makeup. Got it? To put it in terms that would be more familiar to high school students, especially those who just came back from the prom. Okay? The rate of makeup and breakup are equal. You've got an equilibrium. Got it? All right. Now these are the two dissociation equations for sulfuric acid. these are the two dissociation equations for sulfuric acid. All right? The first one is strong. The second one is weak. Some acids they have more than one hydrogen that can dissociate, but they don't have any of the strong acid behavior. It's all weak acid behavior. Okay? And you saw that list of strong acids, okay, right here. This top line here, that's all your strong acids. Notice only one of these acids has two hydrogens that can dissociate. That's this sulfuric acid here. All these others have just one hydrogen that dissociates, okay? The only strong acid that has two hydrogens that dissociate is sulfuric acid. The only strong acid that has two hydrogens that dissociate is sulfuric acid. Since it has two hydrogens that can dissociate, it's called diprotic. Di meaning two, protic meaning protons, and hydrogens, when they leave behind their electron, become just protons, right? Diprotic. All right? If we have three hydrogens in the acid that can all dissociate, we would call it triprotic. Okay? And I suppose if there were four acid hydrogens that could dissociate, we call it tetraprotic. I'm sure there are some. We don't do well much in high school. Okay? Any questions about the terminology there and what it all means? All right. So the homework I want you to do tonight is to write all three dissociation equations for phosphoric acid. Write all three dissociation equations for phosphoric acid. Now, in addition to this homework problem, we're going to be doing a lab. If you saw your email, you know we have a lab scheduled for Thursday. Okay, now assuming that things don't change and we have to reschedule that, I'm planning on a lab on Thursday, a new lab on Thursday. Tomorrow, we will take a half hour, and only a half hour, out of class for you to finish the solutions, colloids, and suspensions lab. Okay? If it takes longer than that, you can either decide as a lab group that you're going to work in lab while I teach, and then you make up what we do in class, or you're going to come in after school and finish it up, okay? So before you come to class tomorrow, you and your lab group members should sit down and talk about this, either by email or phone or whatever, and figure out what do we got to do, how do we get it done, how do we get it done in fast and furious. Not fast and furious, because we don't do anything in chemistry furiously, okay? But just, fast and efficient. All right? Got it? So make sure you come ready to go. Off the mark, out of the blocks. Okay? Got it? All right. Yes. So, let's talk a minute now about pH. All right? Because we were measuring pH in that last lab. What in the world was that? Well, if you haven't taken the last test, we're going to talk about the extra credit question. So, I'm sorry you don't get to do the extra credit question on the test if you're making it up, because I want to give you the answer, and that's not fair. Okay, I can write you a new extra credit question if you want me to do that. All right? But since we're going to talk about the extra credit question, I can't let you, that wouldn't be fair to everybody else who already took it without knowing about this stuff, all right? Now, in the last unit, we talked about solutions, right? And you had to calculate molarity and molality and percent concentration, among other things, okay? Well, pH is based on molarity. pH is based on molarity. Okay? So, pH, the P part of pH means the negative logarithm. That's all it means. The negative logarithm. Now, technically, when I say logarithm, I don't define what kind of logarithm. It means a logarithm base 10. Okay? So this is the negative logarithm of something. The H part means the molar concentration. of hydrogen ions or hydronium ions. It turns out hydrogen ions and hydronium ion concentration are going to be the same. Hydrogen ion and hydronium ion concentration is going to be the same. And let's go back to our illustration for a minute here and show you why. If I can help you see in a simple way. Every time one hydrogen chloride breaks up, I get one hydrogen ion, right? So the number of moles of hydrogen ions, okay, is whatever moles we get out of this, right? Whenever this breaks up, it makes one of these. So every one of these that breaks up, I get one of these. Remember, moles are counting numbers. 6.02 times 10 to the 23rd particles or something equals 1 mole, right? Whatever the molar concentration of this is, would also be the molar concentration of this. Because every time one of these breaks up, and it's a counting number, you get one of these. Every time one of these breaks up, you get one of these. So if I'm using Arrhenius, this molar concentration is going to equal the molar concentration of this in the Bronsted-Lowry system. Because it's counting numbers. Every time you break one up, you get one. Every time you break one up, you get one. Okay? So if this is the same solution we're making here, okay, the same number of these is what we start with here and here, we're going to have the same number of these as we have of these. And therefore, the molar concentration is the same. Doesn't matter whether you're using a Bronsted-Lowry or an Arrhenius system, the molar concentration will be the same. You with me? All right. So this just means molar concentration of hydrogen ions. Okay? So, if I have, let's say I have 5.00 grams of, well, since we're using hydrochloric acid, let's talk about hydrochloric acid, HCl. And let's just say I have 2.00 liters of solution. Well, I could find the molar mass of this pretty easily, could I not? Okay, so okay. And we've got that in 2 liters, 2.00 liters of HCl solution. So that's 1.37, I'm sorry, divided by 2. And that gives us a molar concentration, because moles of solute over liters of solution is molar concentration. That gives us a molar concentration of 0.0685, okay, HCl, all right? And because every time you put one HCl in water, you get one hydrogen ion. So let's see, that's aqueous. And the chlorine is aqueous. All right. So let's see, 0.0685 moles of HCl. And one of these, right? One of these produces one of those. So 1 mole of HCl, 1 mole of H+. All right? Does that make sense? That's a molar ratio from this equation. Got it? And therefore the molar concentration of H+ is also 0.0685 molar H+. You with me so far? All right then. pH is negative logarithm of this molar concentration. Negative logarithm of 0.0685. And what's the pH going to be? All right, so when I take the negative logarithm of this number, I get this. Of course, that poses the question, how do we round this off with logarithms? Okay? We had how to round off for multiplication, how to round off for addition. Multiplication, division is the same, addition, subtraction is the same. There is actually a third rule for rounding off with logarithms. We're not going to learn a third rule in here. We're going to assume the same role or way of rounding off that we did for multiplication and division for the way we're going to round off with logarithms and exponents. Okay? That's not actually correct. All right, one day when we have time, I'll try to show you the actual correct way to round off for logarithms and exponents, but we're not going to do it right now. Okay, we're going to assume the same rule in multiplication and division we do for this. Yes. What's your question? So in these calculations, then, we're going to assume this same system for rounding off that we use for multiplication and division. So we're going to round to 3 digits because I had 3 significant digits here. So we're going to say our pH is 1.16 is the pH. All right. Now, this only works, what I did here, this simple sort of calculation only works for strong monoprotic acids. This system only works for strong monoprotic acids. All right? Any other kind of acids where you have weak acids involved, then the calculations become far more complex. It's the kind of thing you learn in AP chemistry or in college chemistry. But we won't be spending any time learning those processes in this class. All right? This is an introductory class. You won't be learning those more complex calculations in here. But for strong monoprotic acids, you can calculate the pH directly. Okay? You can calculate the pH directly. You won't have to go through what are called acidization constants to figure out the pH. Or to predict the pH, really. All right, everybody understand what we're doing so far? All right, so here's the main thing I want you to get out of just this. pH is the negative logarithm base 10 of the molar concentration of hydrogen ions. That's the definition I want you to know out of just this part here. Okay? pH is the negative logarithm base 10 of the molar concentration of hydrogen ions in a solution. pH is the negative logarithm base 10 of the molar concentration of hydrogen ions in a solution. Okay? Similarly, or in the same manner, POH. What do you think POH equals? Negative logarithm of base 10 logarithm, negative logarithm base 10 of molar hydroxide ion concentration in a solution. There you go. Okay, one measures hydrogen ions, the other measures hydroxide ions. Okay? These can be thought of as being two sides of the same coin. And in our last lab, I had you guys look at a presentation that showed you how the pH scales and POH scales are related. Remember that? Okay? If you don't remember that, make sure you go back and look at that. You need to know how interrelated POH and pH scales are. Okay? They're two sides of the same coin. They both go from 0 to 14. Okay? If a pH is 14, the POH is 0. If the pH is 0, the POH is 14. Okay? If the pH is 7, what's the POH? 7, because they're both neutral at the same point. Okay? But they're both logarithmic scales. They're both logarithmic scales.